So this problem we've got this time has the curves there, x cubed and x, and it's this time the area between those two curves and 0 to 1 is rotated around the x-axis. Now again, we start to get the idea if we're looking at an annulus type situation, because we're going to get that hole in the middle. So again, what's going to be our curve, our radii for our circles here? So again, if we go across the point x, again, because it's rotating around the x-axis, we're going to have delta x. Okay. Now, for our small circle here, if we go up, again, our point there would be x cubed, and this point there is x, because we go across x and up x cubed and up x. We're going to keep it in terms of x because it's easier than dealing with two different lots of y in this case, because we want it all in terms of x in the end anyway. So our radii here, we go up x cubed, so that's our smaller radius. Our larger radius is x. So that's how we should label our radii in our cross section there. So x and x cubed, which gives us x all squared minus x cubed all squared, or x squared minus x to the power of 6. So pi times that area times delta x gives us our volume. So integrating those ones, not too hard, comes down to 44 pi on 21. So the integration again, pretty easy. This time we've got the area between x and y equals x and y equals the square root of x, so these two curves, and that's rotated around the x-axis. So again, we're seeing the idea that we get our two different radii for our two circles that are being created. So the first, at the point there, that would be the point x, again because it's line y is equal to x. This point here would be x and x square root of x. And notice that square root of x is going to be above x because we're only between 0 and 1. So that's where our limits of integration coming in. Delta x as our thickness, because it's rotating around the x-axis. So we go get our cross-sectional area. There's our larger radius of square root of x, our smaller radius of x. So we put that in. Gives us a volume of pi x minus x squared delta x, and then we're able to integrate that to get pi on 6. So have a look at the integration. Again, not too hard. This one, we've got a slice taken, and we get the area between the x-axis. So x is 0 to 1, and we're going between y is equal to 0, which is the x-axis, and y is equal to x squared. So flatten it out a bit to make it be able to fit in our diagram here, and that's rotated around the line y is equal to minus 1. So again, we've got to pick our points for our radii. So again, if that would be x, so x, and then it's going a distance of 1 there, and this would be a point of x and 1 plus x squared, because that's the point x squared there, but our radii would be from 1, so we get 1 unit here plus the x squared. So there's our two radii that we're going to get, 1 and 1 plus x squared, which again we can put into our area formula for the annulus, expand that out, collect terms, and we get 2x squared plus x to the power of 4. They come out as nice functions here. Pi times that 2x squared plus x to the power of 4 dx, or delta x there, and then we can put it in to do the integral between 0 and 1. Gives us 13 pi and 15. So be careful, get your radii correct, and if you get those correct, everything starts to fit into place. But it's not easy as it seems sometimes to get that radii. Think about it logically, draw a good diagram up, and be able to get that diagram of your cross-section annulus, and you should be able to solve the problem without too many hassles.